Okay, so for those of you who don't have a background in STEM, or maybe this is the first STEM degree you've sought, this may look new to you, and that's totally fine. Many people have been introduced to this in an undergraduate program and wore through 620, which is another core class in the the UMBC IS program. So it may seem a little bit basic to you. And I apologize if that's the case, but we do want to at least make sure everyone is on the same page going into the rest of this lecture. So this section is a little bit remedial, and then it covers some stuff that many of you have probably already seen before. A database is managed by a DBMS, right? So the basic way that a database is accessed happens essentially in this fashion. The user makes a request to some application. The application turns that request into an actual query that can be run on a DBMS. The DBMS parses the query, or interprets the query, depending on the particular parser terminology, and then executes it by looking through a store data accessor first for the definition file or the schema file of the database, and then for finding the actual stored data of the database to return a result all the way back to the user. Okay. This is pretty common even in non-relational databases. You have the same sort of setup. DBMSs work in essentially the same way. The basics end up being very, very similar across all DBMSs. So a DBMS, just to be a little bit more formal, is specialized software designed for a particular application. You can get them on pretty much any computer system that's currently in production. And the expected minimum features for a DBMS: you must be able to create new databases using a schema of some sort. The users have to be able to execute queries to modify the data or retrieve data from the database using the DBMS. The DBMS should support storage of very large amounts of data, and that can be relative to the application. So, for example, a small application on a mobile phone may have a very different concept of what large amounts of data are from a mainframe or cloud-based database. Then finally, you need to be able to control access to the data from many users at once. And users in this case could mean processes on a mobile device, or a actual human user from many different applications on a cloud-based system, or anything in between. Okay, these are the basics of a DBMS. Here's some example DBMSs, and this is a reasonably small selection of mostly relational databases. The last three, MySQL, Postgres, and SQLite, are open source. I'm sure you've heard of some of these before, especially Oracle, which is very commonly used in industry. These are very traditional DBMS systems. Now, you can make a list of other DBMSs, quite a few of them in fact, including non-relational DBMSs. All of them would still operate essentially in the same fashion that we outlined earlier. All right, so components of a database or a DBMS. Store data accessor, that's the part in the middle that's actually querying the data on the disk, including for metadata, schemas, logs, indexes, parts that would be essentially just needed by the DBMS. Query parser, this is the thing that's interpreting the queries provided by the application, optimizing them, and executing them on the database. And then a transaction manager. This is not something that was pictured earlier in the basics graphic that we had earlier. It's just something that logs all of the changes to a database for the purpose of verification and failure recovery, typically doing so in a fashion that allows for, even if the power is just pulled at any given moment, it allows you to maintain some rational state of the database. So, for example, a very easy way of doing this is you would write to a file saying, this is the transaction I plan to execute, and then you would execute the transaction. Once the transaction is executed, you would remove that from the planned file, right? So if the power is pulled after you've written the planned execution, and it's still available on that transaction log, then when the power comes back on, or when you turn the database back on, you can say, oh, they were just about to execute this particular transaction. Let's go ahead and complete that and then move on. Or you could just abandon it and know that you're still in a good state. On the other hand, if you do have power come on immediately after the transaction is completed, then the log has been cleared and you don't have to worry about the transaction. So it's much easier to recover if you have a solid transaction manager. Finally, we need to talk about database roles. In terms of basics, every database is going to have essentially these four roles. somebody who implements the DBMS itself, right, the creator of the DBMS that's managing the database, a modeler who's essentially creating the schema of the database. They're creating ERDs and so on and so forth, relations between the data, finding the most important structural elements of the data that you can organize the database around it. The designer itself, who's generally going to be optimizing and setting up tables and relationships so that the schema can be as effective as possible, right? If the modeler is coming up with a high-level model of what things would look like, the designer is actually implementing this in the SQL or whatever the query is, or whatever their query language is for the database itself. And then finally a user, usually an application programmer who's querying or modifying the data programmatically in some way. So those are the main roles in a database. They exist both in relational and non-relational databases, and you can be more specific than this. This is just intended to give you a high-level understanding of the roles.